Okay, so we have a little bit of practice for some questions that we would see for polymers. The first question says, name the starting monomer and give its structure for the polymer polytetrafluoroethylene. So we're asked for the monomer name and structure. So the first thing we would do is look at the name of this polymer, polytetrafluoroethylene. So poly is the part that means polymer or many. So our monomer unit is just going to be what is after poly. So the name is tetrafluoroethylene. And then we can either draw that because we know what the structure is. It's a little bit weird. Remember, ethylene and ethene are synonymous for each other. Or we can go back through our notes and see what the structure of this is. But the structure is where we have that double bond with 4 fluorines around it. Okay, so you can even make your own practice problems with the other polymers to do this. Okay, and then it says name the monomer used to make polypropylene and draw a portion of the polypropylene polymer. Okay, so polypropylene, meaning many propylenes, so we need to draw propylene. Propylene is prop, is the starting name for it. So prop, 3 carbons long. Propylene or propene is going to be this molecule here. And then we need to draw at least 5 monomer units of polypropylene. So I'm going to just start with a line, and I'm going to put my squiggly line to show that this is not where it starts, but it's the middle of the polymer. And I'm going to draw 1 polymer unit. Let's actually change colors. I'm going to do something a little bit different just to show you guys. So we're going to have, I'm going to start with black. This is the rest of my polymer. Okay, so we're going to have 2 carbons of our alkene. So we have 2 carbons of the alkene, 2 carbons of the alkene. That will be connected to the next alkene. So I'm going to put a black bond to show that it's connected. Now looking at this monomer that we started, I have the 2 carbons of the alkene and I need to show what else is on it. So I have propylene, I need 3 carbons long. So I'm going to put a methyl group here to show this is 1 unit of propylene. We bonded it with the black bond to the next unit. So let's do blue. And then we have another unit. We have our 2 carbons, 3 carbons now. And then it's bonded to the next subunit. Bonded to the next one. Let's do orange, why not? Oh, okay. Okay, so as you can see, we're just kind of going to keep going. I have 5 subunits now, 5 monomer units. So each color that I put here is a monomer unit. Okay, so you can see that it has those 3 carbons. Then each side of the alkene is connected to another monomer. So like right here, this pink one in the middle, one side of the alkene is connected to another monomer. The other side is connected to a monomer on the other side. So my advice for these is to pick either like the downs or the downs going the other way. And those are your alkene units. And then every monomer unit do the same substituent off of it. Okay, so we're looking at these synthetic polymers that I showed you guys in our last video. What are the big 6 polymers? So when you look at, I actually didn't know this for the longest time, so I thought this was pretty cool. When you look at your recycling and they say, oh, we can only recycle 1 through 5, and it has the little recycling symbol. Well, that is because the different polymers have different subunits, and how they recycle those units is different. And so you don't want to put polystyrene with vinyl chloride, because then when they're doing the process to break that down and to reuse it, it's a different process. They have to use different chemicals, and then you would mix those all together and not be able to reproduce and remake that plastic. So I have some facts about polymers here. More than 60,000 plastics are manufactured for industrial use. 75% of them are within these main six that I showed you. The big six is what they call them. There are 233 million tons in 2013 of plastics made in the world, and it's expected to reach 334. So I did not look that up. I'm going to look that up and let you guys know. I didn't look it up for this year or last year, I guess. So we'll see what it is. There's a lot of demand, long story short, in plastics. And so the numeric code in recycling is so that it tells you what kind of plastic it is so you can recycle it better so that we're not wasting and depleting resources in our world. So continuing on, the first one is one we actually didn't talk about. It's ethylene glycol, or there's two different ones, ethylene glycol, or I can't pronounce that one, terephthalic acid. So these are the number one polymers for recycling. But then you see number two is high density polyethylene. Number three is polyvinyl chloride. Number four is low density polyethylene. Number five is polypropylene. Number six, polystyrene. So question for you to think about, looking at the common uses of number two and number four of the big six, high density and low density polymers, or polyethylene specifically, looking at these particular uses of them, see if you can figure out what the difference is. Take a moment, read through these, see if you can notice any kind of clues, or what's similar and what's different about these. So I'll go ahead and tell you. So high density polyethylene is going to be more like high density polyethylene is going to be carbon chains. I'm going to draw like a cartoon right now, but it's going to be carbon chains that are very linear. So when we have maybe that's one polymer, and we have a different polymer, we have another polymer, and another polymer, but they're all pretty flat. So they can squish really, really close together, make high density. These are going to be things that are going to be a little bit more opaque, a little bit stronger. You can't like rip it as very easily. Whereas low density polyethylene are going to be things that are kind of more see-through, or maybe weaker or thinner. So these are things where they're actually branched. And so maybe either there's corkscrews in it, or instead of it being straight, it has different parts that go out, like branching. And because it has all these different parts going out, the polymers can't get close enough together to really pack in. And so that was a pretty bad drawing. I'm going to get rid of that one. They can't pack in very tightly. So they can't, it's kind of like spaghetti noodles. If they're all wiggly and stuff, they don't pack very tightly. But when they're in the box still and they're all straight, they can be right next to each other in the box. And so they take up less space. So high density, they're really straight, so they take up less space. Whereas low density, they could have branching or whatever. So they take up a lot of space. They can't really lock in like Legos to each other. And so they're lower density and easier to rip. They're just not as strong in general. Okay, I think that is where, yes it is. That is where we're finishing up our talk of polymers. I'll give you guys some practice for these kinds of reactions and understanding polymers, and I'll see you guys next time.